Welcome to Thought Frontier.
Hey everyone, and welcome back to the deep dive. Today we're taking a deep dive into quasars.
Yeah, those are really cool.
They are.
Consider this your crash course on these cosmic powerhouses, how they form, what makes them tick, and how they impact the galaxies they live in.
Sounds good.
All right, so
Let's do it.
let's jump right in.
Well, when you look at a galaxy, it's like a whole swirling city of stars, right?
Yeah.
Now imagine pinpointing the brightest thing you can possibly imagine,
Yeah.
something that can outshine that entire galaxy.
Wow.
That's a quasar.
That's incredible.
Yeah, and they're found in the centers of some galaxies, and their discovery story is pretty wild.
Oh, I bet.
Yeah, back in the 1950s, astronomers were doing radio surveys and picked up these super strong signals that at first they thought looked like stars.
But then they realized these things were moving way too fast for anything in our own galaxy.
So something's not right there.
Yeah, something strange is going on.
Yeah.
That's actually how they got their name, quasi-stellar radio sources,
Ah, I see.
or quasars for short.
Gotcha. So they're not just bright, they're insanely energetic.
Oh, yeah.
What could possibly power that kind of output? I've got a feeling it's something pretty massive.
You're on the right track there.
Okay.
Quasars are fueled by supermassive black holes,
Ah, okay.
which are millions or even billions of times heavier than our sun.
Oh, wow.
So picture this, a gigantic whirlpool of gas and dust spiraling into this black hole at incredible speeds.
All right, I'm trying to picture it.
Yeah, it forms what we call an accretion disk, which gets superheated and blasts out light across the entire electromagnetic spectrum, from radio waves to X-rays, you name it.
The whole shebang. Okay, so if I'm picturing this right, the black hole is like a cosmic engine.
Yeah.
And the accretion disk is the fuel that makes it roar. But even the most powerful engines need a source of energy. Where does all that gas and dust come from in the first place?
That's where things get really interesting. You see, when we look deeper into space,
Yeah.
we're actually looking back in time.
Right.
And what we see is that quasars were far more common in the early universe, like way back, peaking around 3 billion years after the Big Bang.
Wow, okay.
It seems like there was more fuel for them to feed on back then, likely because there was just a greater abundance of gas and dust around.
So quasars are like relics from a younger, wilder universe.
That's a great way to put it.
It makes sense, but it also raises the question, why were there so many more quasars back then, and where did they all go?
Well, there are a few theories.
Okay.
One idea is that galaxy mergers were more common in the early universe
Right.
and played a key role.
Okay.
Imagine two galaxies, each with their own supermassive black hole at the center,
Yeah.
colliding and merging.
Oh, wow.
This process could have funneled enormous amounts of gas and dust towards the black hole, igniting a quasar.
So it's not just about a black hole existing, it
Yeah.
also needs that fuel.
Yeah,
You need the fuel and specific events to really get it going.
yeah, got to have the right conditions.
So does this mean that all galaxies go through a quasar phase?
Well, it's possible. Maybe most, if not all, major galaxies hosted a quasar at some point in their history.
Yeah.
It could be like a phase in a galaxy's life,
Mm-hmm.
like the teenage years, full of energy and upheaval.
I like that analogy.
Yeah, and our own Milky Way probably went through a quasar phase billions of years ago before things settled down.
So as a wild child, too.
Exactly.
Wow. I'm starting to see why understanding quasars is so important for understanding galaxies as a whole.
It's a key part of the story.
But if they were so common in the early universe, what happened to them all? Did they just fade away as the universe aged?
That's what we're trying to figure out.
Okay.
It seems quasars have a life cycle, like most things in the universe.
Okay.
We talked about events like galaxy mergers as the trigger. But what happens next? What does that whole life cycle look
Kind
like?
of the whole lifespan.
That's what we're going to dig into now.
All right, let's unpack the life of a quasar then.
Okay.
From what I understand, it all starts with a supermassive black hole and a sudden influx of fuel.
Right. And during this active phase, the black hole grows rapidly as it devours the surrounding gas and dust.
Okay.
But there's a limit to how fast a black hole can grow, you know.
Oh, really?
Yeah, it's called the Eddington limit.
Okay, hold on. Eddington limit?
Yeah.
Could you break that down for me? Sounds important.
Yeah, it's a pretty important concept.
Okay.
It's all about balance, basically.
Okay.
Imagine you're trying to eat a giant bowl of soup, but you've only got a tiny spoon.
Oh.
You can only eat so much
Right.
at once, right?
It's true, yeah.
It's kind of similar with black holes.
Okay.
They pull in matter with their immense gravity, but the radiation they blast out can also push matter away.
Uh-huh.
The Eddington limit is that tipping point where the outward pressure of radiation balances the inward pull of gravity.
So even black holes can get overwhelmed by their own meal
Exactly.
if they try to eat too much too fast.
They can't just gobble everything up at once.
That's a powerful image. I like that.
Yeah.
But eventually the fuel supply has to dwindle, right? What happens when a quasar starts to run out of gas and dust?
Well, eventually the quasar activity dies down and things settle down.
Okay.
The black hole might continue to grow slowly, but the intense quasar phase is over.
Uh-huh.
It's like the embers of a dying fire, the
Yeah.
energy output dwindles, and what's left behind is a dormant supermassive black hole, like the one quietly residing at the center of our own Milky Way galaxy.
It's like it's taking a nap after a big meal.
Exactly.
That's fascinating. It seems even the most powerful objects in the universe eventually reach a state of equilibrium.
Things settle down eventually.
But before they fade away, quasars leave a lasting impact, don't they? I mean, all that energy and radiation must have some effect on their surroundings.
Oh, you're absolutely right. Quasars, despite their small size relative to their host galaxies, can have a profound impact on the environment around them.
Okay.
And that's what we're going to explore next.
Sounds good to me. Let's zoom out a little and see how these cosmic powerhouses shape the galaxies they inhabit.
Let's do it. You know, it's like this cosmic dance, really. Yeah. On the one hand, you've got this incredibly powerful quasar just blasting out radiation and particles,
Yeah.
which can heat and push away gas.
Uh-huh.
And on the other hand, you've got the galaxy,
Yeah.
which provides the fuel for the quasar in the first place.
Right.
It's this intricate interplay that shapes how both of them evolve.
Okay, so if we're talking about the quasar affecting the galaxy, how does that actually work?
Wow.
We know galaxies are full of stars, gas, and dust, right?
Right.
So where does the quasar's influence come in?
It's kind of like a gardener with a leaf blower.
Okay.
The quasar's intense radiation and those outflows, they can heat up the interstellar medium, which is the gas and dust between stars.
Uh-huh.
And this can actually prevent new stars from forming.
Whoa, so it's like a cosmic spring cleaning.
Yeah.
The quasar is clearing out the building blocks of stars
Hey.
and preventing the galaxy from actually growing.
You got it. But it's not just about clearing out the gas.
Okay.
The energy from the quasar can trigger these powerful winds that actually blow gas out of the galaxy completely.
No way!
Yeah, it's like a cosmic hurricane.
So the quasar is having like a huge effect then.
Yeah, it's pretty dramatic.
Yeah, that's a good word for it.
It's removing the materials you need to form stars.
Okay, so this influence is pretty dramatic then, but how does this all connect to what we actually see when we look at quasars today?
Well, that's where things get even more interesting.
Ooh, I like interesting.
Astronomers are using these large-scale surveys, like the 2DF and the Sloan Digital Sky Survey,
I've heard of that one.
to map the positions and properties of millions of galaxies and quasars.
So it's like creating a 3D map of the universe
Exactly.
with quasars as like the brightest landmarks.
Precisely. And one of the things these surveys are showing is that quasars aren't just randomly scattered across the universe.
Oh, really?
No, they actually tend to cluster together. And the way they cluster can tell us a lot about their lifespan and how they relate to the large-scale structure of the universe.
Hold on, cluster together. What does that even mean?
So think about it like this. If quasars are long-lived, meaning they stay active for a long time, they would hang out with these rare, massive structures called dark matter halos.
Dark matter halos, okay.
Yeah, these halos are like the scaffolding of the universe.
Mhm.
And that's where galaxies and clusters of galaxies form.
So if quasars live for a long time,
Yeah.
we should see them clustered in these massive rare halos.
Exactly. But if their lifespan is short,
Yeah.
then you'd find them in more common, less massive halos.
Ah, I see, I see.
So by observing how quasars cluster,
Yeah.
we can get a sense of how long they typically live.
So it's like a cosmic detective game?
Yeah, basically.
That's really cool.
Yeah.
So what have these surveys shown us so far? Do we have a good estimate of how long a quasar typically stays active?
Well, right now the data suggests a lifespan of around 10 million years.
10 million, wow.
But with upcoming surveys like the expanded 2DF in Sloan, we'll get an even clearer picture.
That's awesome.
Yeah, and that's going to be really important for understanding how both quasars and their host galaxies evolve.
It's crazy how we can get all that info just from where these things are in the universe.
I know, it's amazing what you can learn just from their distribution.
Yeah, like they're telling us a story.
Right.
But I'm curious, beyond just that big picture of quasar clustering, what else are astronomers hoping to learn about quasars going forward?
Well, one of the biggest questions is how the luminosity of a quasar, so how bright it is,
Yeah.
relates to the mass of its host halo.
Okay.
Basically, we want to know if brighter quasars live in bigger cosmic houses.
So does a quasar's energy output correspond to the size and mass of the structure it lives in?
Exactly. And if there's a strong correlation there, it would tell us even more about how quasars form and evolve.
Okay.
And the 2DF and Sloan, they're going to be key to figuring that out.
That's cool. It seems like there's so much more we can learn from them.
Oh, yeah, tons.
Okay, this is all super fascinating, but we've been focusing on this big picture.
Right.
I want to get into like the nitty-gritty details.
Yeah.
We've talked about the black hole, the accretion disk,
Mm-hmm.
but I've heard about these powerful jets that shoot out from quasars.
Oh, yeah.
What can you tell me about those?
Quasar jets are one of the most visually stunning and powerful phenomena associated with quasars.
I bet.
Imagine beams of incredibly energetic particles, mostly electrons and protons, shooting out from the poles of the quasar at nearly the speed of light.
Oh, wow. That sounds like something straight out of a sci-fi movie.
It's pretty wild.
But how are these jets even formed? What's propelling those particles at those speeds?
It all comes down to the extreme environment around a supermassive black hole. As material spirals inward, it forms the accretion disk. But some of that material gets caught up in the black hole's magnetic fields, which are crazy strong. And these fields act like a cosmic particle accelerator,
Whoa.
channeling energy and matter outwards in the form of these powerful jets.
So it's like a cosmic slingshot then,
Yeah,
with the black hole's magnetic fields launching these particles into space.
you got it.
How far do these jets go?
They can stretch for millions of light years,
Millions.
piercing through the interstellar medium, and even hitting galaxies far beyond the quasar's host galaxy.
That's mind-boggling. They must have a big impact on the space around them then, right?
They do. They're not just shooting off into the void.
Okay.
They actually shape the environment around them.
How so?
These jets can heat up gas in other galaxies, trigger the formation of new stars, and even influence how those galaxies grow and evolve.
So it's not just the quasar itself that's affecting things.
Right.
It's these incredible jets, too.
Carrying the energy far and wide.
It's like everything's connected out there.
Absolutely. It really highlights the interconnectedness.
Quasars and their jets are such a testament to the power and complexity of the universe.
Couldn't agree more.
And it seems like the more we study them, the
Yeah.
more we're learning about how galaxies form, evolve, and interact.
I think what's really striking is how important gas is.
Okay.
It's the fuel for the quasar,
Yeah.
but it's also the building block of stars and the interstellar medium.
Right, so it's kind of a balancing act then.
Yeah.
The quasar needs gas to survive,
Right.
but its activity can disrupt the gas supply for star formation.
It's a delicate balance for sure.
And how this balance plays out affects how galaxies evolve over time.
Exactly. Like, for example, some studies are suggesting that the energy released by quasars can actually regulate star formation in their host galaxies,
Oh, wow.
preventing them from forming stars too quickly and using up all their gas.
So it's almost like a thermostat,
Yeah,
controlling the temperature of star formation in the galaxy.
that's a great way to think about it.
Yeah.
And this feedback mechanism,
Yeah.
it's what makes the relationship between quasars and their host galaxies so interesting.
And complicated.
Yes, very complex. It's amazing to think about these forces interacting on such a vast scale.
It is.
But it's not just a one-way street, you know.
Oh, right, right.
The galaxy also influences the quasar.
Okay, how so?
Well, things like the amount of gas in the galaxy, how it's distributed, how it's moving, all of that plays a role in determining how bright and active the quasar can be.
So it's that cosmic dance again.
Exactly. It's a two-way street.
Both partners influencing each other.
Yeah, and understanding this dance is crucial for understanding how galaxies evolve.
I'm starting to get a better sense of how quasars and their host galaxies kind of grow up together.
They do. They co-evolve.
But we've been talking big picture again.
Right.
I want to hear some of the smaller details from your research. Like,
Yeah.
what's something that would really pique our listeners' interest?
Well, one area that's really cool is the role of mergers in triggering quasar activity.
Right.
Remember how we talked about galaxies colliding and merging in the early universe?
Yes, and you said that those mergers could funnel gas towards the central black hole
Yeah.
and basically turn on the quasar?
Exactly. And recent studies are backing this up.
Oh, wow.
A lot of the most luminous quasars we see,
Yeah.
they seem to be in galaxies that have recently merged.
So two galaxies crashing together can cause a quasar to shine brightly.
It's like adding fuel to the fire.
And the early universe was so chaotic.
Oh, yeah.
So it makes sense that lots of quasars back then were triggered by these mergers.
Exactly. That makes a lot of sense.
Okay, so we've established that mergers are a big trigger for quasar activity.
Right.
But what about something else I've heard about? Their variability.
Ah, yes, quasar variability.
Yeah.
One of the most fascinating and kind of confusing parts of these objects.
Yeah, they're not just shining steadily.
Yeah.
Right?
Their brightness fluctuates over time.
So they're like cosmic strobe lights.
You could say that. Their luminosity can change over days, weeks, even months.
And why is that? What's going on there?
That's what we're trying to figure out.
Okay.
It can tell us a lot about the physics of the accretion disk and the black hole itself.
So what are some of the theories about what's causing these fluctuations in brightness?
Well, one possibility is that the accretion disk itself is unstable,
Okay.
which leads to changes in how much material is falling to the black hole.
So it's not just a smooth, steady stream.
Right. It's more like a cosmic traffic jam, with clumps of gas and dust bumping into each other, changing the flow.
So those changes affect the brightness.
Yeah, these variations in the accretion rate can cause changes in the quasar's brightness.
Okay.
Another possibility is that the black hole's magnetic field is interacting with the accretion disk,
Okay.
and this creates hot spots that flare up and fade away.
So it's like a cosmic lightning storm.
Exactly.
And these magnetic flares can also contribute to the quasar's variability.
That's right. And there's even some evidence that some of this quasar variability might be caused by gravitational lensing.
Gravitational lensing. Yeah. Remind me what that is again?
Remember how we talked about gravity warping space-time?
Yeah.
Well, if you have a massive object pass in front of a quasar, its gravity can bend the light from the quasar, making it look brighter for a bit.
So it's like a cosmic magnifying glass.
Exactly. And that lensing effect can cause dramatic fluctuations in the quasar's brightness.
Wow. So many things can contribute to quasar variability.
Yeah, it's a lot.
It's like a puzzle, figuring out which thing is happening in each case.
It is, but it's also a really useful tool. Yeah, we can use it to study the physics of accretion disks, black holes, and even the structure of the universe itself.
It's incredible how much we can get from these flickering lights from so far away.
I know, it's pretty amazing.
And we're getting better at it all the time, right?
Oh, yeah. With new instruments and techniques, we're learning more and more.
I'm excited to see what's next.
Me too.
Okay, so we've covered a lot. From the basics of quasars to this intricate relationship they have with their host galaxies.
It's been quite the journey.
It has, but there's one thing you brought up earlier that I want to go back to. The idea of failed quasars.
Ah, yes, the black holes that almost made it.
Yeah, it's a fascinating idea.
It really is.
But is there any evidence to support that they actually exist?
Well, it's a pretty new idea, and we haven't actually seen any failed quasars yet.
Okay.
But there are some theoretical reasons to think that they might be out there.
Like what?
Remember the Eddington limit, that balance between gravity and radiation pressure?
Yeah.
Well, some black holes might not ever reach that limit.
Okay.
So they never become full-fledged quasars.
And why not?
Well, maybe a black hole is in an area without much gas. So it can't accrete enough material to get going.
Okay.
Or maybe the black hole is spinning too slowly, and it can't create powerful enough jets to clear out the gas.
So there are things that can stop a black hole from becoming a quasar.
Exactly.
Like they have to pass certain thresholds.
Right.
And some just can't make it?
Yeah. And there are other things, too.
Oh.
Maybe the black hole gets messed up by interactions with other black holes.
Okay.
Or it hits a really dense patch of gas that smothers it.
So there are a bunch of ways it could fail.
Exactly.
But how do we even find them if they're so hard to see?
That's the big challenge.
Yeah.
We're still trying to figure out how to identify them.
But if we do,
Yeah.
it'll change everything we know about how black holes evolve.
For sure.
Yeah.
It would give us a whole new perspective on them.
It would raise so many new questions, too. It's like we're about to uncover this hidden chapter in the story of the universe.
It's very exciting.
Yeah.
Yeah, it really is mind-boggling when you think about the scale of it all.
It is. But let's take a step back for a second.
Okay.
Why should someone who isn't an astrophysicist care about quasars?
That's a good question.
I mean, they seem so far away, like so removed from our everyday lives.
That's a question I get a lot.
Yeah.
And it's a fair one.
Yeah.
But quasars, even though they're super distant, actually hold clues to some of the biggest questions we have about the universe.
Oh.
Yeah. And our place in it.
Okay, I'm listening.
Remember how we were talking about how most galaxies, even our own Milky Way,
Yeah.
probably had a quasar at some point?
Yeah, like it was just a phase.
Exactly. When we study quasars, we're basically looking back in time at our own galaxy's history.
Oh, wow.
We're seeing its wild, crazy youth
That's cool.
when it was full of energy and changing like crazy.
So quasars are like a time machine.
You could say that.
We can see our galaxy billions of years ago.
That's the idea.
And if we can figure out what was driving those quasars back then, we can learn how our galaxy formed, how it got its shape, how it became the place we know today.
Exactly.
It's like looking at baby pictures of our galaxy.
I like that.
But it's not just about our galaxy, right? It's about all galaxies.
The quasars can tell us about how galaxies evolve in general.
Right, because of how they influence them.
Exactly. Remember how we talked about quasars heating and expelling gas?
Yeah.
Regulating star formation? Even triggering the formation of new stars in other galaxies.
It's all connected.
It is. And those processes are fundamental to how galaxies change over time. By studying quasars, we learn about the things that control the galaxy's growth, its star formation, even the elements within it.
Wait, elements, like the stuff that makes up our planet and us.
Exactly. The heavier elements, the ones that aren't hydrogen and helium, they're made in stars.
Right.
And quasars, they influence how those elements get spread around the galaxy.
So they helped create the building blocks of life.
In a way, yes.
It's amazing how these distant things are connected to our origin.
It really is. It shows that we're all part of something much bigger.
It makes you feel small.
But also connected.
Yeah, it's crazy how much we've learned about quasars in such a short time.
I know. It's amazing how far we've come.
Well, I think we've done a pretty good job diving into the world of quasars today.
We covered a lot of ground.
We did, from the basics to how they affect galaxies.
It's been a really interesting journey.
It has. And to our listener, thanks for coming along with us.
Yeah, thanks for listening.
I hope you've enjoyed learning about these incredible objects and all their secrets.
It's a fascinating field.
It is. The universe is full of wonders.
Absolutely.
Keep exploring, keep asking questions, and never lose that sense of awe.
Couldn't have said it better myself.
All right, everyone, that's it for this deep dive.
Until next time.
Happy stargazing.